What is the relationship between physics and consciousness? The traditional viewpoint in science is that everything is reducible to the physical level. Chemistry emerges from physics, biology emerges from chemistry, so it's natural to assume that somehow consciousness too might be explained in terms of biology and neuroscience, the study of the brain and the nervous system, and ultimately then too be reducible to physics. But exactly how this would work remains a seemingly intractable mystery. Well, perhaps the solution to this mystery is not that we haven't yet found the correct answer, but rather we are asking the wrong question. What if consciousness doesn't emerge from physics, but physics emerges within consciousness? How would this be possible? Does this even make sense? And what would that look like? Well, I'm going to be answering some of those questions later in this video, but before we do that, we need to take a quick overview of the traditional approach to physics and some of the key developments and ideas over the last few hundred years, starting with Isaac Newton.
Newtonian physics uses simple equations in terms of parameters like position, velocity, and acceleration to model the dynamics of observable physical systems. Examples include the trajectory of cannonballs, skateboarding, launching rockets into space, anything that involves the motion of macroscopic everyday objects that we're used to seeing in the world, as well as the force of gravity responsible for falling apples and the moon orbiting the Earth. Newton's equations use concepts like force, mass, and acceleration, and the mathematics of differential calculus, which models rates of change, to describe physical dynamics. The dynamics of things we can observe and measure with simple instruments like rulers, clocks, and weighing scales. A fair bit later than Newton, in the early 19th century, a new physics was discovered, that of electromagnetism. With it came the notion of the field, which is basically just a mathematical concept involving numbers or vectors or other mathematical objects existing at every point of a space that the field occupies. The electric and magnetic fields were understood as fields of mathematical vectors that interacted with each other to produce a variety of observable phenomena such as electricity or electromagnetic waves like radio or visible light. By 1865, James Clerk Maxwell had codified the laws of electromagnetism into 4 equations, which, like Newton, sought to describe aspects of the physical observable world, although this time in terms of the rather more elusive fields, as opposed to the forces and massive objects of Newton. In the later part of the 19th century, physicists, including Maxwell and others like Helmholtz, Gibbs, and Boltzmann, came up with an entirely different way of doing physics that used statistical concepts like temperature and entropy. Tragically, while Boltzmann was largely shunned by the academic powers that be in his time, leading to his eventual suicide, today we understand thermodynamic systems like gases or liquids in this kind of language. While this involves a completely different mathematical approach to that used in the mechanics of Newton or electromagnetism, it still speaks fundamentally in terms of some kind of system that you might measure or observe in a laboratory or the world around us. The statistical approach looks at systems in terms of microstates. These are underlying states of the system about which we do not have or need to have full knowledge, but which we speak of in average or statistical terms. For example, the temperature of a gas in a simplified sense can be thought of as the average of the energies of the underlying particles that make up that gas. To talk about the temperature or to measure the temperature, we don't need to know the energy of each individual particle, just some notion of this average quantity. The entropy of a system, in units of Boltzmann's constant, is given by the logarithm of the number of states or ways of configuring the system. Essentially, this just means that the more possible configurations a system can have, the higher its entropy. Colloquially, people often relate this concept to the disorder or complexity of a system. Strictly speaking, we again don't know all the details of the microscopic goings-on, just be able to talk about how many ways the system can be configured in this case. This set or space of possible configurations or states is called, unsurprisingly, the configuration or state space of the system. The notion of an abstract space of possible states is a very important one for this video. It's also an idea that was built upon in the early 20th century with the advent of quantum physics, and it's also very central in the mathematics of dynamical systems, which we'll get into in a minute. In quantum theory, the state space is known as a Hilbert space. This is a type of vector space, which is a mathematical concept similar to the notion of physical space, which you can describe using the kind of axes like you might be used to seeing on a graph, but we're not talking about physical space, rather the space of possible states, which is just an abstract notion. It's definitely a bit of a tricky concept if you've never encountered it before, and don't worry, I'm going to use a simpler example of a state space when we talk about dynamical systems to explain it better. But suffice to say now that even in quantum physics, we're specifically talking about an external physical system that can be in some state, and rules about how it may change that state, and the probability of the outcomes of various measurements we could make. However, in quantum theory, experiments in the early 20th century already began to reveal that there was a bizarre conundrum that nobody had ever considered before. From Newton to Maxwell to Boltzmann and everyone along the way, physics had always done just fine making reference only to these measurable physical systems as if they were independent and highly predictable, with a nature of their own. In quantum mechanics, it became apparent with the introduction of the Heisenberg uncertainty principle that observer and observed are intrinsically and inextricably linked, to the point that one can't meaningfully talk about the observed system without making reference to the observer observing that system.
Separation of the observer from the phenomenon to be observed is no longer possible.
The mere act of observation has a non-negligible effect on the result of that observation, although this is only noticeable at extremely small scales like that of the size of atoms or smaller. The measurement problem in quantum mechanics is a question regarding the nature of quantum objects like electrons or photons, and how they behave when they're not being observed versus when they are being measured. Imagine you have a friend who is super unpredictable and does random things when no one is looking, but the moment you start watching them, they choose one specific action and stick to that. That's kind of what quantum particles do. In quantum mechanics, particles can exist in multiple states at once, a phenomenon called superposition. For example, an electron can be in multiple places or spinning in different directions simultaneously. But when we measure it, say to check its position or its spin, it suddenly picks one option and shows that one option to us. Before measurement, it's as if the particle is in all possible states at once, and the act of measuring forces it to settle on one state. The big headache is why and how the act of measuring makes the particle go from being all over the place to just one spot. It's like the universe is saying, okay, now that you're watching, I'll make up my mind. Now, while many of the early quantum physicists like Planck, Bohr, Schrödinger, Heisenberg, von Neumann and Wegener considered the role of the conscious observer in this situation to be paramount, the physics community these days generally doesn't give it the same significance. Despite the unavoidable fact that all we can and ever will know is conscious experience, so you may well ask what the universe even is, or what matter or energy even is, if not merely a way of talking about conscious experience. In fact, I made an entire video all about that called What is the Universe, so check that out if you're interested. I also made a video called Don't We Understand Consciousness, in which I explored, among other things, the so-called hard problem of consciousness, one of the most challenging, outstanding problems in modern science and philosophy, which asks how we can ever reduce subjective qualities of experience like colors or feelings to physical things like brain states or electromagnetic or even quantum interactions of matter. Why does red look like red instead of blue, and why does fear feel like fear instead of love, and things like that. So go check that video out if you want more information on that one. This denial of the significance of consciousness and the observer also flies in the face of every experiment that has been done testing for realism in quantum mechanics, i.e. something that is completely independent of the observer. Experimental tests such as the EPR-like experiments and the measurement of Bell's inequalities have made the case worse and worse for realism. Einstein believed there should be some kind of hidden reality behind quantum mechanics, and had a long argument with Niels Bohr about it over many years. But every single test so far to this day has sided in favour of Bohr's position that reality is completely observer dependent, and in fact that the physical world and observer must be considered as one single combined unit. As it currently stands, realism isn't technically completely dead according to empirical evidence, but local realism is. In 2022, the Nobel Prize for Physics was awarded to Alain Aspect, John F. Clauser, and Anthony Zeilinger for their experiments with entangled photons separated by large distances, and the demonstration of what Einstein called spooky action at a distance. Their work, collectively spanning decades, provides strong evidence against the classical assumptions of local realism, as well as closing various loopholes. Local here basically just refers to space. So, in other words, science has now shown that if there is any kind of observer-independent reality whatsoever, it can't depend on space-time. So, how can any of this make any sense? Well, as previously mentioned, legacy physics has always considered an external physical system to be fundamental, and that's the framework where all these problems arise. There are, however, some cutting-edge researchers who are paving an entirely new way of doing physics, one that not only naturally dissolves both the measurement problem and the hard problem of consciousness, but also unites science with the perennial wisdom of the age-old teachings of spiritual traditions like Taoism, Hinduism, Buddhism, and others. It's compatible with the insight gleaned by the millions of people who have had mystical experiences or experienced degrees of spiritual enlightenment on Earth today and in the past, as is very well documented across many cultures. And this new branch of science might just turn out to be the crucial key in the next step of humanity's evolution. Welcome to the wonderful world of observer-centric physics. To get an idea of how this works, it's helpful to first be familiar with the idea of a dynamical system. This is the chaotic double pendulum. It's just two pendulums connected end to end. The very predictable single pendulum just swings from side to side and gradually approaches a final rest state of hanging directly down in the presence of friction. The double pendulum has a far more complex behavior. It's so sensitive to initial conditions that it's practically impossible to predict what it's going to do, and its behavior over time can vary dramatically, performing all kinds of intricate flips and flops until eventually also returning to rest under friction. Every time you drop it, even from an almost identical position, it does something different. So we have a two-dimensional space that contains every possible state or configuration of this system. Every point in this space corresponds to a set of two values for the angles and therefore a state of the double pendulum. We can then consider possible paths or evolutions over time of the system. If we had a triple pendulum, we'd have a three-dimensional configuration space, and so on. Each degree of freedom requires an extra dimension of this abstract space. And we can really apply this way of thinking to many possible systems of greater complexity. Perhaps another nice example is a mannequin or the human body. All the different joints provide different degrees of freedom to move and take up any possible configuration, and the space of all these configurations is the configuration space of the system. But just as we can think of the body as a dynamical system, if we think about the conscious experience as having a specific state of experience at one time, and an evolving timeline corresponding to a dynamical path through the configuration space of the conscious observer, we have a way of mathematically modeling this journey, which is what we as observers would experience as life. Now, I mentioned experiments have shown that reality can't depend on space-time, and in order to understand how to think about the universe from the observer-centric perspective, it's important to understand what a non-space-time dynamical system means. The double pendulum, or say the physical body, moves about in space-time as the parameters change. But take a look at this. On the left is a color wheel, and on the right is displayed the color corresponding to the position of the dot in the color wheel. Since the color wheel is two-dimensional, the dot can move left to right or up and down. The color on the right can be considered the state of the color disk, while the color wheel shows the configuration or state space of the disk. As the dot moves around, the disk changes state, and that's what we see as a change of color. But this has no reference whatsoever to physical spacetime in this sense. The state of the system is, in this case, just what the color is. Similarly, we can think of a TV screen as having a state, which is mathematically a set of pixel values for red, green, and blue at each point on the screen. So, watching a video on the screen, you are watching one of the possible routes through the abstract, non-physical space of possible images that could be displayed on that screen. So, in observer-centric physics, our fundamental parameters would be degrees of freedom of the sensory experience, a kind of generalization of the notion of an image to encompass the other senses like sounds, feelings, taste, smell, and possibly other things we're not even aware of. When you play a virtual reality game, you're well aware that this experience has some kind of mathematics to it because the game is written in computer code, but you wouldn't be suckered into the illusion that there is anything there in the sense of local realism, speaking of things being really localized and there. Of course, watching a screen, you do perceive space and things changing in space over time, but this is emergent rather than fundamental. It's all created by a signal being fed in, controlling the light-emitting technology in the screen, and the fundamental parameters are pixel values. Those pixels have space-time coordinates on the screen, but when somebody throws a ball, there is no ball changing its position over and above the pixels lighting up. It's all in the mind of the viewer. But then you may well be wondering, how do we get the measurable and observable physics we know from the observer-centric assumptions? Well, a few years ago, a groundbreaking paper was published by physicist Markus Müller, who showed how simple mathematical relationships between binary strings can logically lead to the probabilities associated with what an observer sees next in their experience, based on their current state. In the paper entitled Law Without Law, From Observer States to Physics via Algorithmic Information Theory, Müller also showed how observers in his framework end up experiencing the kind of external world we see, complete with measurable physical laws, just by considering these properties of binary strings and what happens when observers, whose conscious states are described by binary strings, interact with each other. The space of possible binary strings represents all conceivable states or pieces of information that could exist. This space is vast and potentially includes all possible configurations of information. So the space of binary strings would correspond to the state space of the conscious observer. It turns out that the structures of the binary digits themselves do automatically predict the world that we see without the assumption of any fundamental space-time degrees of freedom. A truly remarkable result. That basically means that everything we see around us in the world can equally well be described just by the dynamics of conscious observers, rather than thinking at all about some kind of external physical world. Another scientist, Donald Hoffman, professor in the Department of Cognitive Sciences at the University of California at Irvine, has been developing observer-centric understanding of reality for several decades. His ideas center on the proposition that what we perceive is not the true reality, but a user-friendly interface that helps us navigate the world more efficiently from an evolutionary standpoint. His theory posits that objects and entities we observe in the world, including notions of space and time, are just iconic representations, not the true underpinnings of reality. In recent years, Hoffman and his colleagues have been developing a mathematical model involving what he calls conscious agents to describe how conscious experiences and interactions might fundamentally constitute the fabric of reality. He proposes that space-time itself emerges from the interactions of these conscious agents, not dissimilar from a multiplayer VR headset game. Hoffman connects this idea to quantum mechanics using a geometric object called the Amplitudhedron. The Amplitudhedron is a way to calculate the probabilities of particle interactions without getting into the gritty details of space-time and particles themselves. It simplifies the math by focusing on the geometric shapes formed by these probabilities. The Amplitudhedron was first introduced in 2013 by theoretical physicists Nima Arkani Hamed and Yaroslav Trinker. They presented it in their joint paper, which outlined how this geometrical structure could simplify calculations of particle interactions. They discovered that this geometric object could describe particle interactions more simply and elegantly than the standard methods involving Feynman diagrams, which are typically complex and computationally intensive. This discovery was significant because it suggested that aspects of quantum field theory could be derived from purely mathematical properties of these higher dimensional geometric shapes. This was a step towards a potentially deeper understanding of the universe that doesn't depend directly on physical space and time at the fundamental level. Since its introduction, the Amplitudhedron has stimulated considerable interest and further research in theoretical physics. It has prompted discussions and additional studies into how space-time and unitarity, fundamental properties of reality as described by quantum mechanics, emerge from the deeper geometric structures of the universe. Hoffman relates his theory of conscious agents to the Amplitudhedron via another mathematical concept called decorative permutations. I'm not going to go into these rather beautiful technical details in this video, but let me know if there's enough interest I might do a deep dive video on these ideas. Essentially, though, the idea is that by modeling conscious agents interacting with other conscious agents, we can derive the fundamental probabilities of quantum theory directly, without there ever needing to be a separate world in some kind of state, unless that state is merely taken to be the state of the conscious observer. In upcoming videos, I'm going to be applying the dynamical systems framework of the conscious observer to talking about the notion of spiritual awakening, both individual and collective. So make sure you hit that subscribe button because it gets really bonkers what we can actually make sense of and even predict with some pretty straightforward reasoning when we start thinking in this observer-centric way. And I mean the actual shared conscious experience we are having right now. I hope you enjoyed this video. If you do, please let me know. If you don't, please let me know. Also, hit like, share with a friend, have a great day, and I'll see you next time.